So, welcome to my presentation that I'm going to deliver in collaboration with my two colleagues, Dr. Fabiana Lisco and Mr. Nick Goffin, entitled Reducing the Energy Payback Period for Photovoltaics. Now, this project is an independent project still funded by EPSRC, whose activities are actually strongly aligned to the project in which I'm the lead researcher, called Eco-Intelligent Manufacturing. So we are going to see the update of this Eco-Intelligent Manufacturing Grand Challenge project, then introducing this specific project, laser annealing of photovoltaics, and then my two colleagues will talk about the deposition techniques of this new generation of thin film photovoltaic cells and the laser processing techniques. So, as Professor Rahimifard already mentioned, currently manufacturing decisions are currently based on cost, time, and quality. What we are actually need to reach is to obtain eco-aware manufacturing decisions. Well, this can be obtained by acting on three different ways, which actually correspond to the three different timescales of decision-making: short, medium, and long-term. Short-term means increasing the automation through the implementation of better sensing technologies, and for the medium and long-term decision-making, we have the design of key performance indicator and management and control systems, which will create a series of eco-informations, and together with the automation, we can reach eco-aware manufacturing decisions. The first case study I'd like to really briefly introduce to you is in collaboration with General Motors. And this is an application of eco-intelligent manufacturing concept applied to engine block manufacturing process. The technology is the cupola casting. Again, the short-term decision-making in this case is represented by a tool which is able to give the breakdown of energy components for this cupola process in order to keep under control the embodied product energy. In terms of medium-term decision-making, we're implementing an energy dashboard for the prediction of the energy consumption, which is extremely important for this kind of companies, especially if we think to the kind of contract they have with their energy supplier. So they have to be able to forecast the amount of energy needed, and in case they consume more or less, well, they have to pay a fine. So the energy prediction is extremely important, process-wise as well. And for long-term decision-making, one, let's say, case study, one specific sub-project we are developing is actually the shift planning within this manufacturing context. The shift planning, we aimed at minimizing the environmental impact in terms of energy, waste, water consumption, and so on. The second case study is the cleaning in place monitoring. Cleaning in place is a procedure that manufacturing companies adopt in order to clean the industrial equipment without the need of disassembling. Currently, unfortunately, most of the companies just follow some best practice based on statistics, but mainly based on feelings. So they run the washing cycle for half an hour because statistically it's clean. What we are developing is actually a monitoring system. In this case, the specific case is the ice cream manufacturing. So imagine these big tanks which need to be cleaned. We are going to develop a system endowed with UV light, spray balls, and you can see also the general scheme here, and the vision system, a camera, wide-angle camera. This system will allow us to keep under control the fouling removal rate, as well as the cleanness assessment. As you can see in this picture, the 4 different phases of a cleaning process. At the beginning, then during the washing, during the rinse, and when the tank is clean. This is, of course, the impact of this project is, of course, to minimize the utilization of water, the utilization of chemicals, and above all, to reduce the cleaning time, because if you're cleaning, you cannot produce. And the next project is the laser annealing of photovoltaics. Currently, the new generation of thin film solar cell, this is the new generation presents some drawbacks. First of all, they are very high energy. They require a lot of energy to be manufactured, these solar cells. And we are actually talking about 1 gigajoule per square meter of thin film cell. 1 gigajoules, but 46% of this extremely enormous amount of energy is represented by the cadmium telluride layer, which is extremely thin layer, 2 micron over a general thickness. The total thickness is 6 millimeters. Well, the cadmium telluride is a growing market, and represents currently 6% of the global PV market. But these, the drawbacks are that the process is slow, requires very high temperature, and is very energy intensive. So the approach we are going to use is still based on 3 different methodologies. The first one is focused on the deposition techniques. We are going to use the pulse DC magnetron sputtering that my colleague will illustrate very clearly later on. The laser annealing for the activation of the device, and this is the novel, extremely novel methodology. And then we can also draw some energy consideration about the cell for the evaluation. So the impact that we are going to reach, hopefully. We need to reduce the energy required for the manufacturing of these PV cells by 30%. 30% means that based on the previous statistics of 1 gigajoule, so we are going to hopefully reach 700 megajoule per square meter. And if we apply this saving, the same saving to the current global market, we are going to save something like 800 gigawatt hours, which corresponds to 1 month of power station. The energy resilience also is fundamental the system should be resilient to the energy shocks. So the brownouts, the blackouts, we need to use the uninterruptible power supply. And also the potential of the reel-to-reel production and different substrates, like flexible solar panels or transparent solar panels. And again, in this project, we still can identify 3 different decision-making levels. The first one is the short-term, the process monitoring. What does it mean in this case? For example, during the manufacturing, one common problem is the formation of defects in the solar panel. And we are going to see how it's possible to keep it under control to avoid defects. And also the annealing process monitoring, which requires some particular techniques that my colleague Mr. Goffin is going to introduce you later. The medium term is the flexible productivity of these PV cells, production planning based on energy availability. And long term, as you know, this technology will enable the manufacturing of new products. These, for example, flexible solar panels, transparent solar panels. So these new products will require, obviously, some new business models, which need to be resilient. And now I would like to give the word to my colleague, Dr. Fabiana Lisco, which will talk you about thin film PV cells. Thank you.
Thank you, Alessandro. So I'm going to talk to you about thin film PV cell, showing some deposition techniques for cadmium telluride, and in particular introducing the pulse DC magnetron sputtering. So why cadmium telluride thin films technologies? We know that this process can achieve really high efficiency, and nowadays, First Solar has achieved record efficiency, which is 21.5%, which is really close to what crystalline silicon technology reached, which is 25%. It's a long-term stable process with the potential for low-cost production. So because of cadmium telluride properties, and in particular I'm talking about physical and optical properties, we can deposit a really thin layer of material, which is around 2 microns. So this means that with this kind of technology, we can save time, energy, and material. We can choose, actually, among different deposition techniques. And in particular, talking about high vacuum systems, we have the closed space sublimation, the vapor transport deposition, and the conventional sputtering, which is the radio frequency RF. But they show particular drawbacks, which are related to high temperature needed, and these are quite slow processes. On the other side, we have non-vacuum techniques, and we can choose among electrodeposition, screen printing, and chemical buff deposition or spray deposition. But, as I said, we have drawbacks, and in particular for this kind of technologies, the deposition rates are extremely low. That's why we decided to use a novel process, in particular it's a novel application for photovoltaics. It's an high vacuum method called pulse DC magnetron sputtering. Why? It's a stable process without arcing. It doesn't need complicated matching circuits, which are needed instead for the conventional RF sputtering. We can achieve high deposition rates, so that's why it's an industrially scalable process. There's the option for working at room temperature. We can think about an inline process, so by using just this machine that you can see here, we can produce the whole device, so the front contacts, the layers that we need to obtain the device, and the back contacts. We can load different substrates, and we can even use a plasma source for substrate pretreatments. So we can control different parameters like deposition time, the gas that we're introducing, frequency, power, and temperature. But we have talked about cadmium telluride solar cells, but still I didn't know what is it. So we call it a substrate configuration because the light has to strike the glass, which is the first layer. On top of the glass, there's a conductive layer, which is the front contact of the cell. Then the light goes through cadmium sulfide, which is the N-type window layer, reaching the absorber layer, which is the thicker part of it, cadmium telluride, and finally the back contacts to close the device. But in order to make this device a proper working device, we need an activation treatment. And nowadays, usually it has been used cadmium chloride as a post-deposition process by solution or evaporation. But we know that cadmium is a toxic material, so our challenge now is to replace this toxic material with magnesium chloride, which is a non-toxic one. And now my colleague will explain you, in particular, the activation treatment, which is based.
Thank you very much. Okay, so laser processing. There's a couple of aspects to laser processing, which I'm just going to go through very quickly. The first being laser inspection. So during the optical measurement is a recognized technique already in other applications, mainly, for example, fume analysis or engine PIV, sports technology, for measuring particles in a medium, usually particles in a gas or a liquid. A novel application for this being its use in cadmium telluride thin films, where it can be used to detect voids, pinholes, stacking faults, etc., which are shown here. So voids, on an SEM image of the layer, here's some voids, stacking faults. Shine a light through it, you can see pinholes. These are all flaws that appear during the manufacturing process and can cause degradations in the performance of the cell. So we have certain advantages to using an optical inspection system versus using an SEM or an electron microscope system. First one being that we can do it without moving the sample. So in situ, in a production process, we can shine a laser at it and we can measure the production flaws in progress. It can be done at high speed and in real time. So we're shining a laser, a camera is essentially videoing it with some computer software doing rapid image analysis as we go along, and it allows the panel quality to be inspected during production. So we don't have to pull samples off the production line and then spend hours preparing them in order to put them into an electron microscope. We can do it very quickly while the production process is going on. Then we can tweak the settings, production settings, parameters at the time to keep it under control. So for this, we require a certain amount of equipment. We need an infrared laser, then an infrared filter, which is just used to control the output of the laser beam so it doesn't overload the camera. We have a cadmium telluride sample, and then we have a CCD-based camera itself, which is the experimental setup shown here. So the laser fires the beam through the IR filter, through the sample, and then into the camera. And that produces an image that looks like this. So objects interfering with the beam create diffraction rings. So the laser spot is in the center, and then rings appear around the outside. Objects is defined as anything that gets between the beam and the camera. So that can be particles of dust in the air, it can be stray reflections from any surrounding equipment, and it can be flaws and pinholes in the cadmium telluride sample itself. So the equipment is fairly simple, it's fairly low cost, it's quite rapid. So the next question is, how do we isolate the cadmium telluride? Well, what we do is we create baseline images. So we shine the laser into the camera in place without having a cadmium telluride sample in place. And that gives us all of the data from all of the ambient diffraction sources, and we get baseline images. We then subtract the baseline image from the raw image of the cadmium telluride to create a combined image which subtracts the baseline from the cadmium telluride and shows us just the cadmium telluride. So this is the image as it looks like when you shine a laser through a panel into a camera, and this is what it looks like after we've subtracted the baseline. From there, we can create image histograms, which are shown here for closed space sublimation and pulsed DC magnetron sputtering. And you see there's the differences in the images, which are then analyzed using a neural network decision making to characterize the samples and identify which ones are which, so it can be automated. And this was done using 80 samples, and we achieved 100% success rate. So the next part of this is laser annealing itself. So we're using a laser to post-process the sample after the cadmium telluride has been deposited. So for this, we created heat transfer simulations in order to analyze in advance what different laser beam profiles would achieve. And we created this sample, which has a Tech 15 glass layer, 3,000 microns, and then the 3 coated layers of transparent conducting oxide at 0.05 microns, cadmium sulfide at 0.07 microns, then cadmium telluride at 2 microns. To give you an idea of the scale of how thin this is, that's the whole panel. And then if we zoom in to a picture less than a pixel thick there, we can see the cadmium telluride layer and then the very, very thin other layers. We then create a mesh, which looks like that, which has 110,000 elements covering all of the layers. It's a 20 by 20 millimeter panel, so it's quite a lot smaller than the physical ones, but that's purely to reduce computing time and actually hopefully complete the simulation before everybody dies of old age. Then what we do is we use some what are called holographic optical elements. So these are a new type of optic, which has been used for other material. We've used it for other material processing applications. This is the first time it's been used for cadmium telluride. And what it allows us to do is customize the profile of the laser beam to optimize heat flow. So a standard laser beam is what's called a Gaussian shape. So it's a circular spot. This is a circular spot, like this laser pen, and the heat is concentrated in the center. So a Gaussian laser beam, circular spot, uneven heat profile. This is not good for materials processing because what it gives you is an overabundance of heat in the center and very little heat on the outside. So you get thermal gradients in the substrate, you get uneven heating, which means you get uneven annealing. So the inside will be over-annealed, the outside will be hardly annealed at all. What we then do is we use a holographic optical element, and what this does is it reshapes the laser beam. So you get constructive and destructive interference within the beam as it reflects off the mirror, which allows us to then create an optimized heat profile. So this particular heat profile is optimized for laser hardening. This is a metallurgical application and gives a flat heat profile across the width of the beam rather than the overheated central one that this would give. So then if we run simulations comparing a Gaussian beam to a pedestal beam, which is a circular Gaussian spot versus what is essentially a flat square, we get this. So here we have a circular spot, lots of heating in the center versus very little heating on the outside. And it's much narrower than this one, even though the beams are actually the same width, because the heat effect on the outside of the beam here is not enough to actually warm the substrate up. And then we can go a step further, and we can compare a pedestal beam versus what's called a peak edge line. So it's much narrower lengthwise. And we put little heat spikes at the edges, which compensate for the additional conduction at the edge, which reduces the curvature. So we get a much flatter, more rectangular heat profile. And that looks like this. The idea of this being to eliminate as much extraneous heating as possible. So instead of using current processes, using an oven, for example, where you heat the entire panel up, all we're doing is heating the top few hundred microns. So so 3/4 of the glass is no longer heated, which reduces the energy use. So what we're due to do now is we're due to start actually testing these in experiments. So we have a laser on its way, which is 35 watts at 808 nanometers. We have holographic optical elements in production, and we have cadmium telluride samples in production. So to summarize, we've discovered that there's a significant opportunity to reduce the energy payback time in photovoltaics. We discovered that pulse DC magnetron sputtering is the most suitable for this, for high quality deposition, and it's scalable, so we can do big panels, small panels, experiments, production. We have a potential to reduce the toxicity levels by eliminating cadmium from one of the post-deposition processes and substituting it with magnesium. We can use optical sensing as opposed to high expensive electron microscopes, which gives us a low-cost, high-speed manufacturing inspection process. We've discovered that holographic optics give us the ability to control the heat flow in thin film annealing, which allows us to reduce the energy use, and we're due to start experimental activities shortly. Thank you for listening. All right.